Greetings, ladies and gentlemen. Today we will look at a feature called shear flow in a makeup cross-sectional area. My name is Julapot Jirawacharade. This lecture is a part of a thought course of Mechanics of Materials at International Program in Civil Engineering, King Mongkut University of Technology, Thonburi.
Last time we already discussed the effect of the transverse shear stress, proof according to the relationship with the longitudinal shear stress. However, we haven't actually discussed the effect of the longitudinal shear stress itself. Right? I want to demonstrate here by using these two books. These two books are in fact the same width, if you can see. So at this edge and this edge at this time will be at the same level. But once I bend it, you will notice that there was still becoming certain gap between the two books here to see the edge here, right? Then, in fact, what it means is that it actually can slide if we just actually put it on the top of a charter. Of course, in terms of civil engineering, we cannot allow that, because it means these two books do not actually take the force together. It behaves like two different cross-sectional areas. So we have to find a way that it has to deform together and do not sliding across the surface of each other. If you look at the picture on the left hand side now, we can show you the normal type we do. We can use the welding or maybe glue if the two part welding for the metal, or even glue for the metal if we have a strong enough epoxy glue. And if it's the wood, then it cannot be weld, then we can use glue instead. And we decide the strength of those weld or the line of the glue, so that make sure that it doesn't slide. Or if we show in the bottom here, is that maybe we don't want to use the whole glue system or welding system. We can use a nail for wood or bolt for wood or metals, right? So these are kind of things that we can do to guarantee that the cross section will behave together, the material will behave as one.
Before we start formulating for the equation of shear flow, I like to clarify certain things so that we don't get confused along the way. First off is that the shear flow, in fact, is causes general concern about sliding along the length of a member, especially when you have two cross section that made up of two pieces or three pieces of material. How do they gonna behave together, right? Shear flow, however, is not a stress. They are related to longitudinal shear, and the unit is force per length. Notice the unit is force per length because it's more convenient on we working on that rather than the shear stress, which is the force per unit area, and it becomes less useful as you're gonna see in the calculation a little bit later. Now, we'll pick up the proof from where we actually almost cut off to calculate the shear stress, though it's the same concept, right? Therefore, and again, I have to emphasize here that the value of longitudinal shear and value of longitudinal of the transverse shear stress are the same, right? So the proof will be similar. There's no doubt about it. So we left off where we proved last time, right? To cut so that we can see the shear, but this time we don't want to see the shear stress, we want to see the shear flow instead, right? So there we are. Now, because the shear flow itself is already per length, right? Force per length, what length, right? Is the length of the beam per length of the beam. Therefore, to make it a force is time the length. It's not the length in the depth of the wheel, but in fact it's the length of the x. Again, the length of the beam, along the length of the beam, right? Therefore, we don't need the bottom wheel this time, right? But the other things are the same, right? So the right hand side, we still have to find out what is a prime, and of course, we have to designate the point where the stress we are looking at for the sigma and sigma prime, so that we know how to set up the integration equation for the force in the x direction. Again, it actually restricted the same way we restrict the shear stress, because we take out the shear force from the picture, or the shear stress from the picture, the transverse one, of course. Right. So the next step is set up the same way we set up for the shear stress. However, the difference is the next line is that although we derive the force from sigma and sigma prime the same way, the force from the shear flow is not the shear stress. So therefore, we don't time the total area. We just time the length along the beam, which in this case, the element have the length is only dx. Right. So it's the force for shear flow is q times dx, the little q. Right, and then the whole step here follow the same argument all along the way from last time, and because of the bending moment doesn't change with y or z, right, it change with x, and we don't move x at the moment. X is fixed at one point, therefore bending moment can take out of that integral, right? And you know, integration, the same integration gives us the same thing, the first moment of area, y bar prime times a prime, substitute it back. Oh, this is the area we're talking about, right? Rather than having the picture right on the top or on the left hand side, which is the top right of the left hand side, right? Rather than talking about y prime and the a prime with the integration, we can reduce it to y bar prime times the area a prime itself, right? Which is a more familiar term that we work with. And of course, differentiation of bending moment by dx, the word is by dx, where it varies with, then we get the shear, right? And we have a simple expression for the shear flow, right? Q equal to VQ over I, right? I is the same I that we used before, the area moment of any shear, which is the total area, not A prime, the total area A, right? So let's summarize a bit. The shear flow causes the sliding between two connecting material. So we have to prevent the sliding so that make sure that the cross-section area work like one piece of material, right? Otherwise, all theory we talk about will break too, right? They have to work together as a single unit. The second point is about the equation we find out the magnitude of the shear flow, right? Where how we calculate the first moment of area, and of course the definition of the area A prime is where we look at and then take either side of the area. Now the point of concern, notice that it preventing the sliding between the connecting material. So the point of concern is now fixed to where the connection of the materials are, right? But well, that's the general idea. Let's look at how we solve the problem then. Okay. Let's look at an example. This example is the same example we used the last 2-3 lectures already. Right? I just change the cross section now into, rather than having a one piece of material like a homogeneous one, now we have two pieces, the one on the top, right, the one at the bottom, right. It took basically two pieces to make up a T. One is the top of the T, one is the leg of the T, right. So the question simply asks that if it's only one type of material, in this case I call steel, but it could be any one type of material, right? So I have to emphasize that it has to be one type, otherwise we run into problem with composite material if we can tackle later on, right? So the question is this: to make sure that it doesn't slide, right? If we use a bolt, right, one bolt at a point with 10 centimeters apart spacing, right? What is the requirement of the bolt? The second one is, if we don't use a bolt, then we weld it, right? We weld it on the left hand side and the right hand side, right, of the leg of the T to make it connect. So what is the minimum requirement strength of that welding? Of course, in this case per length, right? So let's see how we put shear flow in action and calculate all these requirements. Of course, before we can do anything to resist shear flow, we need to know the amount of shear force we need to resist first, right? So the first step is to calculate those first. And to calculate the shear flow, we need to calculate the shear force, the first moment of area, and the value of the area moment of the shear, I, right? So let's go bit by bit. But this one we have seen already on how we calculate the shear. Usually, because as in normal cases, if we have so little choice, we tend to use only one type across, right? But have to make sure that only one arrangement will resist the whole thing. Simply, it's simpler in terms of construction, right? Rather than having so much grading, right? So let's say we're going to use the same strength of the nail across the beam, and also if we weld it, we're going to use the continuous welding, not by gapping, right? Just the whole length. So let's see how it goes. Now we have the shear force diagram. In this case, again, to make sure that whatever we do can resist the whole beam of the whole beam, we use the maximum value. Again, maximum in this case, I mean the absolute value, right? So in this case, we still use the 225 kilonewtons shear force. Now we identify what the shear force we will use. So the next step is we're going to calculate the area moment of inertia. This one here, we don't know where the centroid is. Again, the area moment of the shear, I emphasize so many times in the shear stress, is that we use the whole cross-section area, not the cut area. Never. Okay. In these two fields, the stress by bending moment and anything that to do with the shear stress, we're going to use the area of the total area, right? So we have to find where centroid is, the centroid is, so that we can measure the distance between the centroids, and then we calculate the area moment of inertia. Then we move on to calculate the first moment of area Q, right? Now this one here, where we choose the point, is important. Again, we have to understand that the shear force resisted at the connection. It doesn't resist. We don't want to resist shear force, shear flow at any other places, because that is where the sliding occur, right? At where the material connect. So in this case, we will look at the point where it connects between the top part and the bottom part, right? So here's the picture. Again, you can look at the bottom part. It's going to end up the same result. But anyway, so notice that when I cut it and then we look at it, we look at the area A prime now on the top, right? But everything we measure, right? Notice the way we measure the position of centroid is still rely on the neutral axis, right? And once we get our identification correctly, then we can calculate Q quite simply, right? The area is 23/3, and the arm y bar prime already been indicated in the picture, 13.65, and then we can calculate Q. And this is the capital Q, right? The first moment of area. Then we move on to calculate the shear flow with this equation. Then we get the number for the shear flow. As I emphasize, if you analyze the unit, you will find out that this is the force per unit area, not unit length. Sorry, not per unit area, unit length. Right. So let's look at the case number 1. If we have one bolt in every centimeters, right? So each bolt will have to take half the spacing on on the left hand side and half of spacing on the right hand side. So basically, it look after the whole spacing, right? So if there is 5.751 kilonewton per centimeter, 10 centimeter would give it 27.51 kilonewton for bolt, of course, right? And if you look at the cross section, it's only one bolt on the top like that, right? So the minimum required strength would be the number we just calculated. Now, second case then, if we're gonna weld it, right? Let's look at the picture. As I said, it weld on both sides, so meaning there are two lines of welding in this case. In this case, you can weld on one side, or it's gonna look strange, but anyway, you can. But meaning that the whole shear flow per length now is not accepting by just one line. There are two lines of welding helping each other. Ideally, it will take half each, right? So each line will have the strength of half of what we calculate for the shear flow, which is 2.876 kilonewton per centimeter. Right? And these are the answers. And of course, next, if you want to really build this one, you have to go out and find, if you use option number 1, you have to go find a bolt that can take this amount of force, the same as welding. If option number 2, you have to use the either technique or the brand name that actually can guarantee that you have this kind of strength. And that's it for our lesson today. Thank you very much. I appreciate your attendance, and I hope you enjoy learning with us, and I hope to see you again soon. Bye bye for now.